You know that feeling you get when you think you're being watched? Well, in the quantum world, that's not just a feeling. It might actually be changing reality itself. So, let's get into it and unpack one of the absolute weirdest ideas in all of science. This is the big question. Does the simple act of looking at an atom, of observing it, change its story? I know, it sounds like something straight out of a sci-fi movie, right? But a really fascinating experiment from MIT gives us one of the clearest answers we've ever had. And trust me, the result is probably not what you're thinking. All right, to get to the bottom of all this, here's our game plan. We'll start with a little spy story, then get to know Light's two very different personalities. After that, we'll look at a brilliant experiment, uncover its totally surprising answer, and then finally, we'll talk about what it all means for our strange, entangled universe. Okay, first things first, we have to understand this idea of secrets in the quantum world. Physicists have a name for it. They call it which-way information. So imagine a quantum particle is like a secret agent on a mission. If a spy is tracking that agent's every single move, well, we know exactly which path they took. Their final location is a sure thing. That's what getting which-way information is like. But what if the agent moves totally unobserved? This is where it gets wild. They can kind of be in multiple places at once, a state we call superposition. And this ability is what leads to this amazing phenomenon called quantum interference. So the real question becomes, does the very act of getting that information, of spying on the agent, destroy all that quantum weirdness? To figure that out, we're going to need a tool. And our tool is light. But as it turns out, light isn't so simple. It has two completely different ways it can scatter off an atom. First up, you've got what's called coherent scattering. The best way to picture this is to think of a bunch of soldiers all marching perfectly in step. The light waves are all synchronized, totally in phase. And because of that perfect order, they create these beautiful, clear interference patterns. It's the quantum world in its purest, most wave-like form. And then you have the complete opposite, incoherent scattering. Now, instead of soldiers, picture a huge, disorganized crowd where everyone's just moving around randomly. The light waves are totally out of sync. It's just chaos. And that chaos completely washes out any pattern, leaving, well, just a blur. Now here is the absolute key that connects these two. The orderly, coherent light, the marching soldiers, doesn't give away which atom it bounced off. The secret path is safe. But the messy, incoherent light does carry that which-way information. It's almost like the random scattering forces the atom to reveal its position. So this gives us a brilliant way to measure things. We can figure out exactly how much which-way information was created just by measuring how much of that incoherent light there is. So armed with this idea, scientists in MIT came up with this incredibly elegant experiment to finally figure out what really counts as an observation in the quantum world. What they did was, honestly, just amazing. They created a crystal, but not out of matter. It was a crystal made of pure light. They used lasers to create this perfect 3D grid, and they tucked a single super cold atom into each little pocket of this optical lattice. This gave them thousands of perfectly arranged atoms, all held in place, just waiting for the test to begin. And the experiment itself was so clever. First, they get all the atoms set up in the lattice. Second, they fire a really quick pulse of laser light at them. And here's the brilliant part. They measured the light that scattered off the atoms while the trap was still on, and then they measured it again in the split second right after they turned the trap off, which let the atom start to expand. The whole point was to see if freeing the atom changed the kind of light it scattered back. And this brings us to the moment of truth. Pretty much everyone thought the trapped atom and the free atom would act differently, but yeah, that is not what they found. This was really the whole question, right? Does trapping the atom, confining it, having the potential for the trap to know if a photon knocked an atom around, does that actually create the which-way information? And the answer, which you can see right here in the data from their paper, was a total shock. The amount of incoherent light, which, remember, tells us how much which-way information there is, was exactly the same. It didn't matter if the trap was on or if the trap was off. Being physically trapped had zero effect. Just let that sink in for a second. The old way of thinking was that the trap itself was part of the observation system, but this experiment just blew that idea out of the water. The physical trap itself was completely irrelevant. I mean, the researchers said it perfectly in their own paper. The type of light that scattered off the atom had nothing to do with whether the trap was there or not. So, if it's not the trap doing the observing, then what in the world is it? Well, the real answer turned out to be something much more fundamental about the atom. You see, in quantum mechanics, an atom isn't some tiny, hard marble. It's more like a fuzzy cloud of probability, something physicists call a wave packet. And as it happens, the actual physical size of that cloud was the real key to the whole mystery. Okay, let's connect all the dots now. This experiment really forces us to rethink what an observer even is. And the key to unlocking all of this is a famous quantum idea called entanglement.
So here's how it works at the most basic level. When a photon, a particle of light, bounces off an atom, their fates can become linked. They get entangled. The photon flies away, but now it carries a little piece of information about the atom it just hit. That physical link, right there, is the creation of which-way information.
So, why does the size of that atom's wave packet cloud matter so much? Okay, think about it like this. A tiny, squeezed atom is a small target. When a photon hits it, it can't really learn that much about the atom's state, so less information is exchanged, there's less entanglement, and you get more of that orderly, coherent light. But when the atom's wave packet is bigger, more spread out, a photon that hits it can learn a whole lot more. That bigger exchange of information leads to more entanglement, and that creates more of the messy, incoherent light. So you see, it was never about the trap. It was about the size of the atom's own fuzzy existence determining how much of its own story gets told.
And this brings us to a really profound conclusion. The observer in the quantum observer effect doesn't have to be a person in a lab coat. It doesn't even have to be a machine. The observer is any physical interaction, as simple as a photon hitting an atom that creates a record of information and forges an entangled link. The outcome changes not because it's being watched, but because a tiny piece of its story gets written into the fabric of the universe itself. Which, of course, leaves us with one last mind-bending question. If reality only seems to become concrete when information about it is created, then what is the nature of the universe when nothing is looking? When no photon, no particle, no thing is interacting with it, what is real then?